the question on number 6 is, how can we use the circular model to see the equations of motion for a simple harmonic oscillator? Recall that the circular model says, for example, that if the object is oscillating back and forth here, then it's the x component, in its position, it matches the x component of a point moving around a circle of appropriate radius equal to the amplitude of the simple harmonic motion, at angular velocity omega, which is the same as the angular frequency of the simple harmonic oscillator. So how does our model look? Well, if we start at the zero position, the theta equals 0 position, then our angular position on the circle at any instant, it will be omega times t, the number of radians per second times the number of seconds. So that's our position. And of course we're moving at angular velocity omega at every instant. So at this instant we're at this position and we have a speed on the circle that's equal to r omega, the radius times the number of radians per second, as we've seen. That speed, of course, is one part of the velocity, velocity being a vector quantity, so that the magnitude of the velocity here is the radius, which is a times omega. The angle made by this velocity vector is perpendicular to the radial line. This is a right angle here. That's one of the properties of the geometry of a circle. Since the radial line makes an angle omega t with the positive x-axis, because of the direction of motion here, this velocity vector will make angle omega t with the y-axis, again because these two vectors are perpendicular. Okay? Then we have the centripetal acceleration. Okay? The magnitude of the centripetal acceleration is v squared over a. Since v equals r omega, we square r omega and divide by a, we get omega squared a. So the acceleration is always omega squared a toward the center, the acceleration of the point on the circle, not the simple harmonic oscillator. This gives us a vector whose magnitude is omega squared a, and which makes an angle omega t with the negative x-axis, because this thing is in the opposite direction to the radial vector. Now, we see, of course, that our x position is just a times the cosine of omega t. Just looking at the projection here, the projection of this point on the x-axis, we have this triangle, and this side over this side is clearly the cosine of omega t, and we get this very easily from simple trigonometry. If we now look at the velocity vectors, a omega at angle omega t with the y-axis, and omega squared a with angle omega t with the negative x-axis, we immediately see that the x component of this velocity is going to be this vector times the sine of omega t. And that the x component of omega squared a, the acceleration, will be the negative of a omega squared times the cosine of omega t being opposite here in orientation to the omega t by which we calculate the position. So that we immediately get our equations of motion for x, vx, and ax. And those will be the equations of motion for a simple harmonic oscillator moving in the x direction. Okay, next question concerns what are the basic premises we use when dealing with vector quantities, when analyzing vector quantities. And the basic premise is simply that any vector quantity can be completely replaced by its x and y components without any change in the effect of that vector on whatever it is we're observing. Okay, so if we take a force vector and replace it by two force vectors, one for each of the components, one for the x component, one for the y component, it's going to have exactly the same effect on the object that it's acting on as the original force. A velocity vector, if we take the two components of the velocity for a given time interval, we get two displacements, and those two displacements add up to the displacement we would have had for the original velocity vector.